Okay, time for another physics video here. And today what we're going to do is we're going to talk about work and energy. So these are words like we've been talking about with work here that have different connotations from a physics standpoint of view. And the same is true for energy. You know, we say, I don't have a lot of energy, I need some energy. Energy is used in a lot of different ways. But from a physics standpoint of view, energy is the ability to do work. And because of that, the unit for energy is the joule, just like the unit for work is joule as well. As I said when I first started talking about work in that video, if I do 1,000 joules worth of work, it takes 1,000 joules worth of energy, and that's a simplified way of looking at it. One type of energy that's pretty important and central to this video here is mechanical energy. And mechanical energy is two different kinds of energy. And the first one is kinetic energy. So kinetic energy is the energy of motion, and you're probably familiar with that concept already. So the idea of kinetic energy is the faster you're moving, then the more energy you have. And also, the larger the mass, the more energy you have. We could think about this in terms of that idea of energy as the ability to do work. If something is moving very fast and has a lot of mass, and it runs into you, it could do a lot of work on you. But kinetic energy, when you calculate it, as we've already said, has something to do with the mass and something to do with the speed. So there's the formula for kinetic energy. Kinetic energy is 1/2 the mass multiplied by the speed squared. This is a formula that we're going to, for now at least, take for granted. It's a little hard to show you exactly why that's true. So we're going to leave it at that kinetic energy is 1/2 mass multiplied by speed squared for now. Okay, so here's an example. A 25 kilogram object is moving at 4.5 meters per second. What is its kinetic energy? Hey, here's a suggestion. Why don't you pause the video and see if you can solve that. And while you pause it, I will go turn the lights back on. All right, well, did you pause and are you back again? Here's the answer that I got, 253 joules. Let's see how that worked out. Well, as usual, we identify the information, so there is the information, and then we show our work. There's our kinetic energy formula. There are the numbers plugged in with the answer. So how'd you do with that? All right, the other type of mechanical energy is potential energy. And in particular, well, there can be lots of kinds of potential energy. We'll talk about another kind of potential energy later. But an object, just due to its position, has potential energy. Potential energy is stored up energy, energy that is not currently doing work but could do work. So there's a lot of examples of that. But what we're going to talk about now is gravitational potential energy. And with kinetic energy and gravitational potential energy, now you have a really good idea of mechanical energy. We know that work is force multiplied by distance, and energy is the ability to do work. So if you think about this, think about your big toe for a second. If you dropped an object on your big toe, it could do some work on your big toe. It could cause a force to it, that's for sure. And think about this also. The higher that you drop the object from, the more work it could do on that big toe of yours. And also, the heavier or more mass the object has, the more work it could do. We also know that when you lift something up, the force required is the weight of the object. So the force on the way back down is also the weight of the object, and that should make some sense. So let's see. Gravitational potential energy is mgh. mg is the weight of the object, as we've been talking about before, and h this time is the height off the ground. We could use distance here. It would amount to the same thing, but here we're specifically talking about the height off the ground, so we use the letter h. That's a common way to do it. So there you go. mg is the weight, and h is the height off the ground. Okay, so here's an example for you, and once again, why don't you pause the video. This time the light is still on, but when you come back, I will show you the solution. Okay, are you back, and did you give it a try? The answer I had was 2,573 joules. Oh, well, let's see, we got another physics teacher in the room right now. I might get a special guest on the video if we could talk her into it. I don't know. Mrs. Roth, for the record, a fantastic physics teacher in her own right. Want to say hi to the people? Come on over, Mrs. Roth. Here she is. Here she is. This is a real physics teacher right here.
Thank you.
There you go. Very good. Very good.
Normally I get a round of applause.
Yes, well, yes, certainly. I hope at home you are also, you watch this.
Good luck. Good luck with your physics endeavors.
Oh, nice. Hey, that was fun. Oh, now I should charge extra for this video now. Got a special guest star. Oh, boy. Hey, have I ever told you folks I have the best job in the world? She is one of the reasons, Mrs. Roth. Okay, so let's see here. The mass, the height, the potential energy. There we go. Okay, so here's the formula, of course, and then it's just a matter of plugging in the information. So there you go. That's a potential energy. Now, another concept here involved with energy is that energy cannot be created or destroyed. So we can change it from one form to another, and but the idea is it can't be created or destroyed. So this is called the conservation of energy. And for our purposes, we will talk about three things now. We will talk about the total energy, and the kinetic energy, and the potential energy. So total energy for our purposes in these calculations will be a combination of the kinetic energy and the potential energy. It's not exactly true with this stuff. You might lose some energy. Some energy might be lost to air resistance if something was falling through the air or going up in the air. But we're going to simplify it just to say that for this example, these examples, the total energy is the kinetic energy and the potential energy only. You might lose some to friction. You know, there might be some energy loss to friction, but we're going to rule that out of our examples. And the example that I'm using here would involve friction, and that's a snowboarder. The fun thing about snowboarding is you cut down on the friction as much as possible so you can go as fast as possible, but still there would be some losses of energy to friction. But that energy goes into heat and sound, so that energy goes into another form. It's not that we lose that energy. Okay, so here's my example of a 20-kilogram snowboarder. That would be a small child. And when I used to do my snowboarding, there was always some small kids in there. And they were usually a lot better than me. It was kind of discouraging, but good for those kids. So a 20-kilogram snowboarder and a height of 15 meters, what is their potential energy? Well, this is a pretty straightforward one. We've done something like this before. But here what? Their speed is 0. I'm identifying some stuff here. We know what g is. We know their height off the ground, and we know their mass. So we can calculate their potential energy using the formula, the mgh, and we get a potential energy of 2,940 joules. Okay, so how about what is their kinetic energy? Well, we know that kinetic energy is 1/2 mass multiplied by speed squared, and since they haven't started moving yet, they have no speed, and that means they have no kinetic energy. So we can plug in the values there and come up with 0, but it's pretty intuitive as well. You're not moving, you have no speed, you have no kinetic energy. Now, how about our other concept? What is the total energy? Well, the total energy is the kinetic energy plus the potential energy, so we can see that the total energy is also 2,940 joules. Now this is important, so I'm going to say it 3 times. As we look at these problems, the amount of total energy never changes. As we look at the problems, the amount of total energy never changes. And did I mention that as we look at these problems, the amount of total energy never changes? It'll change from problem to problem, but during the course of a problem, and these will be several steps, the total energy never changes. Okay, so how does this work in these problems? Well, I'll show you. Okay, so here's our snowboarder, and we're dealing with the same snowboarder, and now they're 10 meters above the ground. Okay, let me once again put the information down. This time their height above the ground is different, and you know, they're going down the hill, right? So, but their total energy never changes. Did I mention that before? That's central to these problems here. And of course, again, in real life, you'll lose some of that energy to friction and sound, but but we're going to simplify it a little bit. So the total energy for our purposes never changes. So now is my information for answering this question about potential energy, and then the questions that'll follow. Okay, so what is their potential energy? There it is. They've lost some of their potential energy. Have they lost total energy? No, because within these problems, the total energy never changes. So 2,940 is their total energy. Okay, once we find it, we've got it for the whole length of the problem. Okay, so for part C, what is their kinetic energy? Well, what they've lost in potential energy, they've converted to kinetic energy. So, given the information that we have over here, we can see that they now have 980 joules of kinetic energy. Okay, so how about their speed? What is their speed going to be? Well, the kinetic energy is 1/2 mv squared, we know. We now know their kinetic energy and we know their mass. So we are in a position now to solve for the speed. We can divide the 10, and when we divide the 10, we know what v squared is, 98. And of course, what we're going to do is take the square root of that to find out what the speed is. And when we take the square root, it turns out the speed at this point is 9.9 meters per second. Makes sense. They're picking up speed as they lose potential energy as they go down the hill. Okay, and then we'll do one more step. We'll consider the snowboarder at the end of the hill. And at the end of the hill, oh man, they're catching some air over there. This is a picture of me actually snowboarding back in the day. It's actually actual picture of me. Or a random picture that I found on the internet. Yeah, more likely the second one there. Okay, so how about this same snowboarder? They've now reached the ground, and we're going to ask all these questions again. What is their potential energy? What is their total energy? What is their kinetic energy? And what is their speed? All right, the calculations for this part are exactly the same as the calculations for the last part. So I'm not going to step you step by step all the way through them, but maybe you want to pause the video and see if you can get the answers. I will give my answers. Okay, are you back? Well, this is tricky because there's a couple of things that you have to consider here. First of all, now the height is 0 meters. They're at the ground level, so that makes sense. But what people want to say is that their speed is 0 when they get to the ground level. But that will be true. I mean, eventually you'll slow down, you'll stop, you'll go into the lodge, you'll get some hot chocolate, you'll have a good time, you'll maybe warm up by the fire. But when you first hit the ground there, you haven't stopped yet. And that's the speed we're looking for when they're still moving. And it should make sense that that'll be their fastest speed because now they have all kinetic energy. Okay, we remember again that the total energy never changes, so it's 2,940. But now that you have the height and you still have the mass, you can make these calculations for potential energy. Of course, with a height of 0, the potential energy of 0 will be 0. We know that the kinetic energy is going to be 2,940 because there's no potential energy. It's all kinetic energy now. And then we can backtrack as we did in the last problem, and using the square root, we can find out what their speed is. So hopefully you have some success with that. I'll give you my answers now, and if you had some trouble getting them, of course, you can ask questions back in class. So here are my answers for those questions, and hopefully that made some sense to you. Okay, time again to turn on the lights here as I go into my next concept, and that is the idea of work and change in the speed. So this should make some sense too. Hey, that was pretty good. All right, so this should make some sense. It takes a force to cause an acceleration. An acceleration is a change in speed. A force, and it takes, this is going to take some distance that you're applying the force for, well, that's work. So work is equal to the change in kinetic energy. Okay, so I have the symbol, the sum of the work. So if more than one thing was working on the object, we could certainly take that into account. And this symbol with the triangle means a change in kinetic energy. So if you add up all the work, that's working on the object, that'll be equal to the change in kinetic energy. All right, so let's take a look at an example of this. 30-kilogram object is brought to rest, from rest to a speed of 15 meters per second. So we're changing its speed. That's going to take a force. All right, so how much work was done on the object? Well, let's see what we got going on here. First of all, we will identify the information, and you know that work is a change in kinetic energy. A change in anything is your final value minus your initial value. So here we'll have to take the final kinetic energy and subtract it from the initial kinetic energy. That's our change in kinetic energy, and that will be the work that was done. Okay, so let's see how it plays out here. There's my change in kinetic energy. There's my formula for kinetic energy. That's the final speed is involved in the final kinetic energy, and the initial speed is involved in the initial kinetic energy. And I'm just plugging in the information that I've already identified here. And of course, since the initial speed was 0, then the initial kinetic energy was 0 as well. And so that means that there was 3,375 joules worth of work done on the object. Okay. So let's have a follow-up question, and that is, if it took 3.5 meters, what was the force? Well, I know the work, I know the distance, I also know that work is equal to force multiplied by distance, and so I can divide off the 3.5, and I find out that there was 964 newtons worth of force involved. Okay, so there we go. I'm going to give you another problem to try, and maybe you want to pause before you see the solution on the next problem and see how you do. Okay, so here's an object, it's sliding across a surface, so it's coming to rest by friction. There's the information, and why don't you give that a try to find out how much work was done by the friction. Give that a shot. Okay, let's see how you did. First of all, what I did was identify the information. That should be in your notes as well, your complete notes. We know that a change in kinetic energy is the kinetic energy final minus the kinetic energy initial. So as we did before, we can plug what we know here into this change of kinetic energy calculation that we have here. So that means that the work is a negative 112,500 joules. Now it should make sense that it's negative because if the motion of the object is in one direction, the friction works in the other direction, and that would be a negative direction, the opposite direction, and that's why the work came out negative here. Okay, let me give you a follow-up question to work on and see how that plays out. Okay, so there's my distance. What was the force required? Why don't you pause the video and see how you can do with that. Okay, hopefully you gave that a shot, and here we go. I'm identifying the information. I am plugging it into my calculation here, my formula for work. And then with division again, I'm solving for the force, you can see, and I got a force of negative 75 newtons. And again, it makes sense. The force of friction works against you in the opposite direction. So negative 75 newtons. All right, let's see if you can tie in some older concepts to this brand new concept and solve this last one. What is the coefficient of friction? We're tying this into it as well now. I'll give you a chance to pause and see if you can get that solution. Okay, welcome back. Let's see how you did. There is the friction, 75 newtons. Now I know we came up with negative 75 newtons, but we don't usually use a coefficient of friction as a negative value. It's always a positive value. So I'm just saying that I have 75 newtons worth of friction for this part of the calculation, similar to what we've done in the past. And we know friction is the normal force multiplied by the coefficient of friction, and in this case the normal force is the weight of the object. So there's the mass multiplied by 9.8, that's the weight in the normal force. And then we're in a position to solve for the coefficient of friction by dividing off those two numbers, and the coefficient of friction turns out to be 0.15. So hopefully you did okay with that, and if not, hopefully my explanation here helped, and of course if that wasn't working, then you could certainly ask questions back in class again. Okay, so here's another example of potential energy, all kinds of potential energy we could deal with, but a spring that we've dealt with before is an example of potential energy as well. And you can imagine that. If you push a spring down, then while you're waiting, it could start popping up, and that's some work that we could be talking about. So for example, if I have a spring-related toy here, and I push it down there, right now it's potential energy, or it starts off as potential energy, and then it turns into kinetic energy, and then it turns into gravitational potential energy as it reaches its high point. So energy transformations of the potential energy of the spring, then the kinetic energy, and also you build up gravitational potential energy as it goes through the air. So that's a lot of fun. All right, so the formula for the potential energy of a spring is 1/2 kx squared. K is the spring constant that we've dealt with, and x, well, we've always talked about x as the stretching distance of the spring, but it also works for compression. So if you push it down, it's how far you push that down, and I just keep doing that because it's just fun for me. All right, so here is a problem, and are you ready to challenge yourself and try to put this whole thing together? You have all the concepts down, but this is tricky because it's a new situation. So yeah, I would challenge you to do that. Are you ready to do that? To pause and see if you can solve it? I will tell you, I'm looking for an answer in centimeters, that it's 1.9 centimeters. Give it a try. Did you do it? Did you give it a try? Or are you waiting for me to show the solution? It's a tricky one anyway. But once you get it, I think it's going to be okay for you. Well, here's the idea. I'm identifying my information. This is what I know so far. By the way, in the problem I said 5 centimeters. But remember, if I'm dealing, and I am here with newtons, then I've got to be in kilograms and meters. Also, the spring constant is in newtons per meter, so I'm going to need the compression to be in meters as well. And with 100 centimeters for every 1 meter, I've got 0.05 meters. Okay, so let's see, that's the first little obstacle. Now what I'm doing here is I'm showing the idea that the energy at the beginning is equal to the energy at the end. So when it reaches its high point, at that moment its speed is 0, and that means that it's all gravitational potential energy, right? So that means that at the beginning it was all the potential energy of the spring, and then at the end, it was all gravitational potential energy. So that's why I'm equating these two things here. On the left is the initial potential energy of the spring, and on the right is the final gravitational potential energy of the object that goes through the air. Okay, so hopefully that made some sense, but I know it can be confusing. So if that didn't do it for you, bring some questions with you back to class. Okay, so here's my substitution for the information that I know, and this is the calculation, and then of course I'm going to divide, and that gives me the height, and the height comes out in meters because that's the way this was set up as well, and then the conversion over to centimeters. So this time I go in the other direction because I'm converting meters back to centimeters, and that's how I ended up with 1.9 centimeters. So I'm going to turn the lights back on. All right. And so with the lights back on, I will end this video because that's all there is for this one. And I hope it was helpful, and I look forward to seeing you back in class. All right.
Back